So part C says determine the intervals of concave up and concave down and find the inflection points. I'm going to remind myself what the original function was here. That is 2x to the 5/3 minus 5x to the 4/3. I'm also going to remind myself what that derivative was. The derivative ended up being 10/3 x to the 2/3 minus 20/3 x to the 1/3. So that's going to help me find the second derivative, which is what we need to look at to find intervals of concavity. So the second derivative, if I did 10/3 times the derivative of x to the 2/3, that would be 10/3 times 2/3, which would be 20/9. X to the, well, 2/3 minus 1 would be negative 1/3. And then I'd have minus, well, it would be 20/3 times 1/3, which again would be 20/9. And that would be x to the, well, 1/3 minus 1 would be negative 2/3. Well, that's a dang mess, but we should be able to handle it. Again, no more calculus here. All that's involved is algebra at this part. So what is 20/9 x to the 1/3? That's really 20 over 9 times the cube root of x, right? And then minus 20/9 x to the 2/3, that's really 20 over 9. And then you have the cube root of x, but then you have that value squared, right? So what do we have to do to be able to combine this? We need to multiply the first term times what it's missing, which is a cube root of x. And when I do that and I combine like terms, I'm going to end up with 20 times the cube root of x minus 1 if I factor the numerator, times 9 times the cube root of x squared is what we're ending up with there. Wow, what a mess, but it is what it is. And this is my second derivative. Again, the only reason I did that is because I knew I had negative exponents, which means I have a denominator. So I had to get a common denominator and look at this as a rational function. Because again, I need to look, when is this second derivative equal to 0? And when is this second derivative undefined? Well, if it's written as a fraction, it's equal to 0 when its numerator, which is 20 times the cube root of x minus 1 equals 0. Divide both sides by 20 and I would just have the cube root of x minus 1 equals 0. Add 1, I'd have the cube root of x equals 1. Cube both sides and I get x equals 1. So that's a possible inflection point, because it is in the domain of my original function. When's it undefined? It would be undefined when 9 times the cube root of x squared equals 0. Divide both sides by 9 and I'd have the cube root of x squared equals 0. Cube both sides, I'd have x squared equals 0. Square root both sides and I'd end up with x equals 0. So x equals 0 is again a possible IP, inflection point. So what do I need to do? I need to write my interval out here. Again, I'm plugging everything into the second derivative now. I have 2 points. I have the point when x equals 0 and the point when x equals 1. When it's 0, my second derivative is undefined, and when it's 1, my second derivative is 0. I'm thinking about what is my shape of my function. Is it concave up or concave down? So I need to test each interval. The first interval is negative infinity to 0. The second interval is 0 to 1. And the last interval is 1 to infinity. When I do this, and I'm testing this, when I say I need to test it, I need to plug it into the second derivative. The second derivative, again, being 20 times the cube root of x minus 1 all over 9 times the cube root of x squared. I want you to, okay, let's just pick some points real quick. Anything less than 0, I am going to do a cube root of the number. So how about negative 27 again? That works. I need a number between 0 and 1. How about 1/27th? Because I have to do the cube root of it again. And then I need a number between 1 and infinity. Again, cube root, I'll use, how about a 27? I could have used 8s on all of those as well. I don't know, I just know the cube root of 27 is 3. That's something in my mind, so that's why I chose those numbers. Let's think about this. The denominator, always, you're going to take that number and square it, which is positive. The cube root of that's positive times 9 is positive. So no matter what, that denominator, no matter what we chose, that denominator is going to be positive. Okay. So on the first one, what if you did an, oh sorry, this is in parentheses here, that cube root of x minus 1. Cube root of negative 27 is negative 3 minus 1 is negative, times 20 would be negative. So negative over a positive is negative, so that means that entire first interval must be negative. 1/27, well, the cube root of that would be 1/3 minus 1 would be negative, times 20 would be negative. Negative over a positive is negative, so my second derivative on that entire interval is negative. My third interval, 27, cube root of that's 3 minus 1 is 2, times 20 is positive. A positive over a positive is positive. So on that entire interval, it must be positive. So wherever my second derivative was negative, my original function has to be concave down. So it's concave down on the intervals negative infinity to 0 and also 0 to 1. Concave up is any time my second derivative was positive. Well, that would be at the point where, or on the interval from 1 to infinity. So that's where my function is concave up. And an inflection point's wherever it changes concavity, and it has to be in the domain of the original function. Well, every number is in the domain of the function. If you notice at x equals 0, it does not change concavity, so that's not an inflection point. But at x equals 1, we do have an inflection point. Again, though, I need the point. It's an inflection point. So to find that point, I do need to plug it into that original function. And remember that original function was 2x to the 5/3 minus 5x to the 4/3. 5x to the 4/3. I'm going to plug in the number 1. Again, this is already in my table. Not that the number 1 is really hard to plug in anyways. But go ahead and plug in the number 1. And I'm getting the value of 2 minus 5 is negative 3. So that tells me the point 1, negative 3 is an inflection point. The inflection point would be the point 1, negative 3. Sorry, let me close that off. 1, negative 3. Okay. So what do? Now I need to take my information from analyzing the original graph, analyzing the derivative, analyzing the second derivative, put it all onto this one graph, and see what we get. So let's take a look at part A and see what we can glean from part A. So from analyzing the original function, I had both an x and a y-intercept at that point 0, 0. And then I had another x-intercept at the point 125/8, so I went ahead and converted that to a decimal. That's about the value of 15.625. So I'm just going to put that out here and just label that. Again, my scale's not going to be exact on these ones. That's 15.6250. That's my second x-intercept. Again, my y-intercept 0, 0. No vertical asymptotes, no horizontal asymptotes. So that's all I get from analyzing the original function. That's all I can do for my graph. But what I can do now is move on to the first derivative and look at what information I gleaned from the first derivative. What I did with that one is I gleaned that 0, 0 is a maximum. And then we also have this point 8, negative 16. So that'd be roughly about halfway in between those two. Maybe down here I'll just put a point 8, negative 16. And I know that this point must be a minimum, right? Okay. I also know that I need to break it up anywhere and look at the sign of f of x on the intervals. So I'm going to look at that number line and break it up anywhere on this axis here where it was broken up for the first derivative. So look back at your number line on the first derivative, and it was broken up at x equals 0, which we know is a maximum, x equals 8, which we know is a minimum, and we know the derivative went from positive in the first interval, negative in the second, to positive in the third interval. Now we look at anything that we can glean from the second derivative. We know that there's an inflection point at the point 1, negative 3, so I'm just going to plop a little point right here. Sorry, let me do it in black. This is the point 1, negative 3, and again we know that this is an inflection point. Okay. That's all that we have for points, but we do need to break up the graph wherever it was broken up on the number line for the second derivative. Well, it was broken up at 0, which we've already done, and it was also broken up at x equals 1, so I'll drop a line right there. This is going to be really tight. X equals 1 was an IP. And then I look at the sign. Anywhere to the left of 0, the second derivative was negative. F double prime of x, and this was f prime of x, so this is negative. To the left of 0, in between 0 and 1, we notice that it's also negative. In between, or anything after 1, we know that it was positive. So both of these intervals, my second derivative has to be positive. From this, I'm able to tell my shape of my original function, f of x. Okay, on that first interval, which would be negative infinity to 0, I know that the shape of my function, its second derivative is negative, so it's a frown, but the first derivative is positive, so it has to be increasing. So that's going to be the left half of a frown. Second interval, second derivative is negative, I'm a frown. First derivative is negative, so now I'm at the right half of a frown. Third one, my second derivative is positive, so now I have to be a smiley face. First derivative is negative, so I have to be decreasing, so that's going to be the left half of a smiley face. Okay, third interval, second derivative is positive, so I have to be part of a concave up, a smiley face. First derivative is positive, so I have to be increasing, so that's going to give me the right half of a smiley face. So what do? I play connect the dots, making the shape of the graph, what it is, what it needs to be, and go through the points. So to the left of 0, 0, I have to make it the left half of a smiley touching the point 0, 0. Between 0, 0 and 1, 3, the inflection point, I have to make it the right half of a smiley. Between 1, negative 3 and 8, negative 16, I have to connect those using the left half of a smiley. And then anything to the right of 8, 16, negative 16, I have to make a right half of a smiley, but I do have to remember to go through that next x-intercept, which would be something like this right here. So the graph of this function, it looks really weird, but this is what the graph is. Again, what you would use at this point in time is you would go to Desmos to verify this graph. We've actually nailed the shape of this graph on each one of these intervals. We've nailed all the important points of this, the x-intercepts, the y-intercepts, points of inflections, maxes and mins, and again, the exact shape on every single interval. So this is, if you look on the book, they have it all within one page almost instantly. They just say, hey, here's the answer. And again, they've shown absolutely no work as how they got the derivative, the second derivative. They show none of their sign charts. All they did really was just kind of show what we've done horizontally here. They just kind of did vertically with no proof, no work whatsoever shown. And there is a lot of work to be done to get that information. So on the test, you have to show every single one of those steps. I hope that helps.